All right, so we left off. Well, before we jump into it, just as a reminder, so a week from today, at the end of the day, next Friday, you have that Connect and Excel assignment. Really, after last class, you could have worked through. We cover enough to where you have every problem in the Connect. We've went over the material, and we went over everything that's on the Excel assignment as of last Wednesday. So you've got everything you need. Kind of somewhere back where we've talked about it to kind of get through every problem. I'll put up another Learn Smart when I get back to my office today. That'll be due before class starts on Wednesday. So you've got a few days. It should only take like 10 minutes. Just kind of introduce this idea of probability, which we'll start today. And the Learn Smart will probably focus on more of the end part of the material that we'll talk about with probability. But I'll give you a kind of first look at it. So we left off last class. We talked about calculating covariances, using that covariance to calculate correlation coefficients, which we said were between 1 and -1, and told us something about the relationship between these two variables, right? If it was positive, then as x goes up, y tends to be higher as well. If it was negative, that means as x goes up, y tends to be lower, right? And if it's 0, it means as x changes, y doesn't change at all. Excuse me. So, we kind of talked about if it was 0.45, that's not the strongest relationship. The strongest relationship would be 1, right? The strongest positive relationship is 1, but the weakest is 0. So, that relationship between height and weight was kind of somewhere in between. We then said, because it's unitless, because we've scaled it, we can use that correlation coefficient to start to compare the relationships between different variables. Right, so we could compare the relationship between height and weight to maybe years of education and income, right? Whichever is higher, we would say there's a stronger relationship between those two variables, okay? And kind of what we're trying to capture there is this idea that if we were just to look at the data, is there some positive correlation between the two? As x gets higher, does y tend to also get higher? And in this case, it looked like it did. So I had a couple sample questions here that we didn't go over, but I said kind of good additional practice. It should be pretty easy. Once I give you a covariance and I give you the two standard deviations, it's just a matter of plugging them into that correlation coefficient equation. Okay. I don't know if we'll have time to watch this today, depending on how quickly we go through things. But if not, this is a good link that is kind of funny. It's a old Jon Stewart on his old show. It's this economist, he's kind of crazy, and they make fun of him. And it's interesting because part of what he's doing, and we'll kind of return to this idea of correlations later on in the semester, and we have a slightly better way of capturing the relationship between two variables. But what this economist did was he was looking for the correlation between someone's looks and kind of their wage or their salary, right? So he had some work on that, but the kind of more interesting study they did was instead of looking at like wages, they looked at another labor market statistic, which was the number of interviews requested. So they had this group of people and they took pictures for their LinkedIn profile, and then they had like 100 random people kind of evaluate or rank these people based off of looks, right? So they've got these percentiles, right? Each individual was in a certain percentile. They then sent out an identical resume. So every one of these, like, I don't remember how many women and men they had in this study, but for every single one, they created the exact same resume and then made a request. Like I said, I think it was LinkedIn. It was some profile where they were sending their applications in, but they knew the employers were able to see kind of that profile photo. And they found that you kind of see here as the percentile of attractiveness, if they were in a higher percentile, the number of interview requests that identical resume got kind of was higher for women ranked in the higher one. It's also kind of, we can see a positive relationship between that attractiveness and the number of interviews for men, but right, not nearly as steep, right? So all we're really looking at here is kind of the correlation between this X and Y variable. We kind of see this points out that, looks like it's a little bit stronger relationship for women than it was for men, right? Which is a problem. Something as simple as these correlation coefficients can kind of allow us to see evidence that, like, yeah, this shouldn't be taken into consideration at all. This was literally the identical resume, right? But we can identify that problem simply using things like these correlation coefficients, okay? Looking at the correlation between these variables, okay? So it's kind of a review of kind of capping off that subject we talked about last class. We're now going to kind of deviate and go down a slightly different path, right? So we're going to talk about probability. You know, just in general, we talk about things a lot. We say, like, you know, what are the chances that something increases or decreases if something else changes? So here, what are the chances sales decrease if prices increase? What are the odds a new investment becomes profitable? What's the likelihood a new production method or assembly method increases productivity? All of these are really getting at, well, what's the probability that we're going to see certain outcomes, right? So the way that we have to define kind of when we're looking for a probability is we have some experiment. So this experiment just means that we don't know the outcome. So don't think about this. I think you even have a thing here. Don't think about like physics or biology or chemistry. An experiment could be as simple as flipping a coin. We don't know what the outcome is, right? We can run that experiment, the same experiment over and over again. We don't know the outcome. We know what the outcomes could be, but until we flip that coin, we don't know what the outcome is going to be. Or rolling a die, or rolling a dice, right? I know the outcomes could be 1 through 6, but I don't know which one of them is going to come up, right? I don't know what the actual outcome is until I roll that dice and see what kind of number comes out, right? So if we can repeat this experiment in the exact same way over and over, we could realize multiple outcomes. So I roll the dice one time, I see a 3. I roll it again, I see a 4. Right? I can kind of keep repeating this experiment, and the outcome could change every time I run it. So all these different outcomes we could see, we're going to call these experimental outcomes, right? So the easiest one, is think about if I flip a coin, what are the 2 possible experimental outcomes I can see? Heads or tails, right? Rolling a dice. Well, unless I'm playing Dungeons and Dragons or something, right? 1 through 6, right? A kind of conventional dice. So, we've got all these, like, those are kind of our simple examples. But then we can start to think about, well, what if I ask someone, what their age is? Well, there my experimental outcomes start to get a lot wider, right? I'm just choosing a person at random. I could see ages 0 through, 100 and however the oldest person is, okay? So sometimes it's very easy to identify these outcomes. Sometimes it's a little bit harder, right? So the sample space is going to be a set of all the possible outcomes I see, right? So try to paint how these are different. So let's say I've got my dice, right? I know it's 1 through 6. I know those are the experimental outcomes. But let's say instead of numbers, right, there's pictures on there. And I don't know what the pictures are. Maybe they're of animals, right? But I don't know what the 6 animals are. If I only roll that dice twice, I'm only going to see at most 2 of the different pictures, right? So my sample space, I'll only know what the outcomes I've seen are. So my sample space would be, I don't know, maybe I roll it and I see a pig and a lion, right? So that's my sample space. Now there's 4 other possible pictures of animals I could have seen on that dice, but I just don't know what they are yet because I haven't run this experiment enough times, right? If we're rolling a dice, it's like, okay, so just keep rolling it, right? But in different experiments, it may be more costly, right? So we might not be able to repeat this experiment hundreds and hundreds of times, okay? So our sample space is the outcomes that we've seen, even if we know, like even if it is just a conventional dice and I roll it twice, I know the outcomes are 1 through 6 in that scenario, right? But sometimes I might not know what they are if I wasn't able to run this experiment enough and I didn't have prior knowledge to what the possible outcomes were. Okay? And then an event is going to be something that we define. It's just going to be a smaller subset of the sample space. So let's say I roll that dice enough times to where my sample space, I see every number 1 through 6. My event would be, saying something like, well, what's the probability I saw it be a 2 or a 3? So I've defined this event, which is a smaller set of those possible outcomes than all the possible outcomes I saw, right? So I'm kind of just like narrowing in on some specific outcomes, okay? So I think it's kind of a nice visual, thinking about these 3 things in relation. The experimental outcomes, we could draw this huge circle and say, this kind of represents all the possible outcomes that I could see. Right? The sample space will be the outcomes that after I run this experiment a certain number of times, these are the ones that I saw. Right? And then an event is going to be some select number of those outcomes in my sample space. Not all of them, but some subset. Okay? So that shouldn't be anything too bad there. Let me make sure I'm okay. Got paranoid, I forgot to hit record. So, you know, if we're thinking about experimental outcomes, I've already done a couple of these, but if I flip a coin, my outcomes are heads or tails, rolling a die, 1 through 6, choosing a card from a deck. Here, you know, we kind of have to define what we're looking for. So if I'm just thinking about the face of the card, right, not the suit, I'd have ace through king, right? Those are my possible outcomes I could see if I'm drawing a card from a conventional deck. Let's say we're playing a playoff football game, kind of relevant. Super Bowl's coming up here. So I can see a win or a loss, regular season kind of soccer game. I can think about win, loss, or tie, right? So these are, you know, you could think of these as experiments, right? Running kind of the same game. Now, these are pretty basic. We'll start to think about more interesting experiments, but this kind of gets down the idea of, you know, experimental outcomes are any possible outcome that we could see. Okay. Any questions up to this point? Shouldn't be too bad. Good in the chat. All right. So, if we want to give a more textbook definition of probabilities, it's going to be some measure of how likely a specific experimental outcome is once we run this experiment, right? So we're kind of focusing on one specific experimental outcome. The probability is the measure that that one outcome occurs. Okay? The probability of an event, right, is just whatever outcomes are in that event, we're going to add up the probabilities of each one of those outcomes. So here's I don't know. They say it's easy. It's kind of weird to think about. But if I'm flipping a coin, right, we're talking about probabilities. We're thinking about probabilities as like the proportion of time something happens. So our probabilities are going to be between 0 and 1. So if I flip a coin, usually you would say, you know, what are the chances that a heads comes up if I flip a coin once? Most people would say 50%. Right? Well, that's going to be our probability of 0.5. Right? 50% is a probability is 0.5. Okay. So the probability it comes up heads is 0.5. The probability it comes up tails is 0.5. So what's the probability it comes up either heads or tails? Well, intuitively, that's the only two outcomes. The probability should be 1, or it's a 100% chance that I'm going to see a heads or a tails, right? I have to see one of them. And so I'm thinking about if I define the event as the probability of seeing a heads or tails, really what I did there was I added the probability of seeing a heads to the probability of seeing a tails. It just so happened those were the only two possible outcomes. 0.5 plus 0.5 is 1. We'll do the dice example. Let's say I've got this 6-sided dice. I say, what's the probability I roll a 2 or a 3? Well, if there's 6 outcomes, each one's equally as likely. The probability I get a 2 would be what? 1/6. Yeah, right? 0.1866 repeated, I think, right? So the probability I get a 2 is 1/6, whatever decimal, you know. The probability I see a 3 is also 1/6. So the probability I see a 2 or a 3, I just add those together, 1/6 plus 1/6, so 2/6 or 1/3, which makes sense, right? Because it's 2 out of the possible 6 options. Right? Now, this gets a little bit more hairy when we don't have like equal probabilities of the outcomes, but there it kind of gives us a couple nice, easy examples to start thinking about. Whatever outcomes are in the event, I simply take the probability of each one and add them up. And it gets a little bit trickier. We won't get there today, but next week we'll talk about what if we have some kind of overlap with different outcomes, but we'll save that for next week. So when we're thinking about these outcomes, we run this experiment. The way we'll write it as the probability that we see this experimental outcome occur, we'll write that P of E, right? Whatever the experimental outcome is. So the probability I get a 3, or the probability if I flip a coin I see tails, right? We're just writing in the outcome we're looking for there. So these probabilities I kind of already mentioned, you know, the highest they could be is 1. If something is, you know, certain to happen, right? So I say, you know, what's if I don't know, just come up with some weird thing. what's the probability the sun rises today, right? Or something like that. Well, we know it's going to happen, so the probability is 1, right? 100% chance it's going to occur. What's the lowest the probability can be? Well, if something can't occur, right? So let's say, you know, I'm asking, I don't know, people what their eye color is. What's the probability that they respond that their natural eye color is, I don't know, come up with something that I'm sure, I guess I was going to say yellow, but maybe someone's jaundice, right? What's the probability that their eyes are red, right? Well, it's not, we know it's not possible, or whatever color would be an impossible color for your eyes to be, right? We would say the probability is 0. We can't have a negative probability, right? The very lowest chances of something occurring is that it doesn't occur. So 0 out of anything, it would just be 0. Right? So we know this probability lives somewhere between 0 and 1. Okay. Now, if we take every single outcome, every single possible experimental outcome, and we add the probabilities up, those probabilities should add up to 1. Right? Think about it this way. When we were building those histograms and we did the relative frequencies, we were basically saying, well, this is the proportion of times we see, you know, a red car in the data set. And this is the proportion of times we see a green car in the data set. And when we added up those relative frequencies, we said they always add up to 1 because they would take into consideration every single possible outcome, right? That's really what we're saying here. If we take every single possible outcome and we add up those probabilities, they have to add up to 1. There's nothing else we could see other than these possible, you know, whatever experimental outcomes we realize are possible, okay? So the sum of our probabilities of every possible outcome should add up to 1. We'll go over this here in a little bit, kind of give some visuals as well. So we're going to assign probabilities in 3 different ways. So we've got the classical method, we've got, and I'll go through these in more detail here, this is kind of summary, the empirical method, and then the subjective, right? So we're really going to pretty much primarily live in this world using the empirical method, but in some situations, the classical method makes sense, and in others, the subjective method. So we'll talk a little bit more in detail. So the classical method is pretty easy. This is like rolling a dice, flipping a coin. We know that every possible outcome is equally as likely, right? If every possible outcome is equally as likely, the probability of any one outcome is pretty easy to figure out. So if I'm flipping a coin, we had 2 possible outcomes. The probability that either one occurs is 1/2 or 0.5, right? So we had 2 possible outcomes and the probability was 1/2. Rolling a dice, we said there's 6 possible outcomes. The probability any one outcome occurs is 1/6, right? 1/6. It's because we had 6 possible outcomes, so 1/, those 6 possible outcomes. Really all we're doing there, and just so I don't have to switch back and forth here, I'll try to write this, right? 1/, the number of possible outcomes we could see. Kind of think about this as n, right? The different possible outcomes that we could see. So, you know, with the dice, it was 1/6. With flipping a coin, we had 2 possible outcomes, so 1/2. You know, if I'm thinking about the card deck example, I see ace through king, 13 different cards. The probability I get a queen would be 1/13, right? So this one's pretty easy, and I think it's kind of intuitive when we think about assigning probabilities classically, and everything is equally as likely. I think that one's pretty straightforward. Okay. So what if I'm flipping a coin twice and I think about the possible outcomes here, right? So I could get a heads, then a heads, heads and a tails, tails and a heads, or 2 tails, right? So I have 4 different possible outcomes I could see, right, in terms of the ordering. So if I have 4 possible outcomes, the probability, let's say that I get 2 heads would be just 1/4, right? 4 possible outcomes, all equally as likely. So 1/4. Right? And if I add up those probabilities of every possible outcome, so 1/4 plus 1/4 plus 1/4 plus 1/4, they should add up to 1. Right? I've included every possible outcome. Those probabilities should add up to 1. So the classical method kind of makes sense. Right?
Can you find the number of experimental outcomes just by like squaring, what is it, however many events there are?
The number of, so I think when you're thinking about things that are equally as likely, I think what you're trying to say maybe is that if I know the probability of any one event, and I know that they've been assigned classically, to find the number of total outcomes, what I would actually do is look at that denominator, right? 1 out of whatever, right? So if I see this, I automatically know the number of possible outcomes is 4, 1/4, right? You know, if I had something where they aren't classical, that doesn't quite work for me, right? Because depending on which probability I'm looking at, I'm going to think it's a different number. Like if one outcome has a chance of occurring of 1/8, another one is 1/16, another one is a 4th, right? They vary, then all bets are off. But yeah, with the classical method, if you know it's classical, if you know the probability of any one outcome, right, 1/4, you know the number of possible outcomes is whatever's in your denominator. Yep. Is that kind of what you were getting at? All right. So the next one's going to be if we assign probabilities empirically. So I'll give you kind of example and then explain some other ones. So let's say, you know, let's say I had a class of 60 students. And I ask every single person what their favorite type of cuisine is, and 15 of the 60 students kind of respond with Mexican food. And so I've got that 25% of the students kind of were responding with this particular outcome right here. You know, the possible outcomes would be any type of cuisine I can think about. So I have a probability of 0.25 or you know, in percentages, 25%. So what I've done here is I collected some data, right? I didn't ask every single person what their favorite was, but based off the data I see, I know that about, you know, on average, 15 out of 60 were responding with this one specific type of outcome, right? One specific type of food. And so I'm going to say the probability if I asked one person at random what their favorite food is, right, that they would kind of respond with Mexican food here, okay? So I'm using some data to assign the probabilities, right? So, you know, this usually works best if we have like run this experiment a large number of times. So for instance, maybe like the BMV or, you know, whatever I think when I was in Michigan, they called it the Secretary of State, but whoever issues your driver's license, maybe they have data on this, but there's not like a huge database with everybody's eye color, right? But if I go out randomly select 1,000 people and based off of their recorded eye color, I could probably figure out what the probability, if I chose someone at random, what's the probability they have blue eyes or what's the probability they have green eyes, right? And I could kind of assign those probabilities based off that data I had of 1,000 people that I sampled. And that's kind of the idea of assigning probabilities empirically, right? We don't have the entire population data, but we can use some large sample data set to assign those probabilities. And they'll be pretty close to accurate. Okay? Then we have the subjective method. So this is basically like, you're just not randomly assigning, but you basically are saying, I think I know best. I'm going to just say that this is more likely to occur than that outcome, right? But I'll give you an example where that's okay, right? It may seem like, well, you can just put whatever probabilities you want in. Well, let's say a company's hiring a new CEO, right? And there's 4 different possible candidates. Well, we wouldn't want to use the classical method, right? Because Andy here could have already been a CEO and bankrupted 4 companies, right? Right? And, you know, Hill here could be like, I don't know, the next Elon Musk or something, right? And so I don't just want to treat them all as having a 1/4 chance of getting the job. I know that's not true. I know some candidates based off of their resume are likely I shouldn't say that way. Some candidates based off the resume are more likely to probably get this position than others, right? So if I'm, you know, an expert in that industry or in that realm, I would maybe have a little bit better idea about which one of these candidates is going to be more likely to get that role. Right? Now, I can't really use the empirical method here because, like, I can't observe these 4 people applying for the same job over and over and over again. Right? I don't have that data. So sometimes we're kind of stuck with making based off of the, you know, not evidence, but you know, like their resumes and kind of the information we have in front of us, assign those probabilities as best we can, right? Hopefully we don't have to resort to this, but there are some circumstances like this one where that would be kind of appropriate. So welcome to probability and statistics, the class where everything's made up and the numbers don't matter. So I like that. I think this show has started to kind of make some show up. But this was one of my favorite shows when I was growing up. So let's keep going here. Try to get you guys out of here maybe a little bit. We'll see, a little bit early maybe today. I'm going to turn this on. If it screws things up, then we'll have to switch back because I think it'll switch me over. Let's see. See if we can get the slides back up here. All right. So I'll give you a couple quick notations, and I'll kind of show you with some numbers what they actually mean. So the first is going to be if we're thinking about some event A, right? We said these events, however I define them, they at least include one, if not more than one, of the possible experimental outcomes. Okay? So A complement here, A superscript C, we'll think about being everything that's not in event A. So it's kind of like the opposite, right? So if I'm thinking about, if I'm rolling a dice, right, and I think about event A is that I roll a 1, 2, or 3. A complement would be that I get a 4, 5, or 6, right? Everything that's not an A. Okay? A union B, right, we're going to write as kind of with this set symbol, but it looks like a U, right? So A union B, another way we can think of that is A or B, right? So is the outcome in both, is it in either event A or is it in event B, right? If it's in either one, then it's in the union of those two things. Okay? So this we kind of think about, like I said, this is like a U, so union, or the way we say it kind of with our words, A or B. The intersection is the upside down set symbol, or looks like kind of like an upside down U. Some people say, if you put a line through it, it looks like an A. Because the way we read the intersection of two events is it in A and is it in B, right? Is it in both of them, okay? And then the way we read this is A given B. So whatever's on the right-hand side of that line, we say given that this event has already occurred, now what's the likelihood or what's the probability that event A has also occurred? Okay. So this one we'll probably hold off on really diving deep into these conditional probabilities or using this given kind of line until next week. But we'll look at these three today. Okay. So let me see if I can give you kind of a quick synopsis of all this. See if this switches over for us. So let's say, and I'll go over these, we'll go back to those and we'll go over some examples here. So let's say A, we'll use the dice. So let's say it's 2, 3, and 4, and event B is, let's do 3, 5, and 6, right? So this is just kind of all the outcomes that are in events A and B. Just rolling a dice, okay? So if I think about what's A complement, what outcomes would be an A complement here? So remember, the complement is just everything that's not in that event. So if it's A complement, what would be the outcomes that are not in event A? So if in event A, we've got 2, 3, and 4, right? So the what?
So it's just 5 and 6, right?
Forgot one. Literally, forgot one, right? Right? So we've got 1 is not in A, and then 5 and 6 are not in A. What if we wanted B complement? What are the outcomes that are not in B?
1, 2.
Yeah, 1, 2, and 4. No, you weren't wrong. We just missed an easy one at the front there. So that's how we look at complements. It's just every outcome that is possible that's not in whatever we're looking at the complement of. Right? Now, one thing to notice, I'll kind of foreshadow, what outcomes, if I were to look at B and B complement, right? that should include every single possible outcome. So 1, 2, 3, 4, 5, 6. If I look at A and its complement, 1, 2, 3, 4, 5, 6. If I look at an event and its complement, that should cover every possible experimental outcome that exists, okay? So what if I'm thinking about the union of these two events? So we kind of say this is our union, or am I in A or am I in B, right? So how would I write the union of A and B? So is it in A or is it in B? What are the outcomes that would meet that criteria? If I look at these, if I saw 2, a 3, or a 4, that's in A. Or if I see a 5 or a 6, that would be in B. So any of these outcomes are in either A or they're in B, right? So I'm just looking for the outcomes that would belong to either one of those events, right? And if it gets repeated, we don't write it twice. It's still just one outcome, right? So it could be in both, but it's at least in one of them. So the only thing that's, not in this union would be the outcome of 1. Okay. This is a little bit crooked, sorry. We'll see if we can keep all this on the same page here. What if I wanted A intersection B, right? So this is kind of the intersection, or we read it as A and B. Yeah, the only outcome that's in both of these, it's a weird looking 3, right? The only outcome that's in both A and B is the value of 3. So this is how we want to think about intersections, unions, and complements, right? And kind of one of the most basic examples, right? Kind of using just this 6-sided die. Okay. Any questions on that? And we haven't done anything with probabilities yet. We're just thinking about what this notation means. Okay. All right, we'll leave this here for now. Let's go back here. So we've got kind of our notation. We've kind of seen some examples of how it works. Maybe we can get the screen back up here. All right, I don't know what the delay is. So we can have some other visuals, right? So let's say I represent every experimental outcome, every possible outcome is this box, right? Within those outcomes, I could define event A, right, as this circle, and I could create event B as all the outcomes in this circle. Right? So if I'm thinking about the intersection, or what is in both A and B, it's going to be where those two circles overlap, right? All the experimental outcomes that are in both A and in B are going to be where those two circles overlap, okay? The union of those two events, or A or B, is going to be any outcome that's in A, any outcome that's in B, or it could be in both of them. So kind of notice the intersection is actually a part of the union, right? Because the union is just, am I in A or am I in B? I don't care. I could be in both. I'm at least in one of them, though. And the intersection is saying I have to be in both of these events, okay? If we want, well, I don't want to switch over because it'll take it. If we go back to the example we had, our intersection was 3, and our union included the outcomes 2 through 6. So it also included that intersection value of 3. But this is kind of a nice visual using these Venn diagrams, right? So one thing we're going to start trying to use are these contingency tables, right? So these contingency tables try to give me the probability of these different events, right? And we can also start to look at intersections and unions of them. So here we kind of have events A and B. Right? The total columns tell me, the probability of the row and column headings. So the probability of B, I go down to that total, is 0.5. The probability that A occurs is 0.6. The probability that A complement occurs is 0.4. Right? So the totals represent just the probability of the events themselves. The top 4 left cells, right, these guys right here, all tell me intersection probabilities. So it's the probability of the intersection between the row and the column heading. So here, this 0.4 is the probability of being an A and in B, right? Or that upside down kind of U or upside down set symbol. The probability I'm in B complement and A complement is 0.3, right? So I read those top 4 left cells as the intersection of whatever the row and column heading are. I read the totals as the probabilities of just the events themselves. Okay? Any questions on this before we keep moving? Now, one thing we'll kind of notice here is if I look at the probability of A and the probability of A complement, those add up to 1, right? And the probability of B and B complement, those also add up to 1. Right? So why is that the case? Well, and we'll switch over again here. I'll draw it out real quick. If we think about any any example we have, it doesn't matter what the outcomes are, we can kind of, hopefully this is light enough. We can think about this as, I've got all these possible experimental outcomes, right? So this space, if I could think about here's an outcome, here's an outcome, here's an outcome, and I look at every single outcome, if I add up the probability of every possible outcome, those should add up to, what did we say earlier? 1, right? So we can think about it as the space that I've drawn here, this area of this rectangle, all the possible experimental outcomes, the area of this space is 1, okay? Wherever event A is, right? If I think about where would A complement be? Well, A complement would just be everything that's not an A. So every possible outcome not an A. So this would all kind of represent A complement. If I take A and I add to it the area of A complement, I've covered every possible experimental outcome, right? So I know if I take the probability of A and I add to it the probability of A complement, those should add up to this entire space, which had an area of 1. Right? So it doesn't matter where the event is. If we take the probability of an event plus the probability of its complement, we'll always fill out every possible space or all the possible experimental outcomes in that space. So an event and its complement, those probabilities will always add up to 1. And I think we'll talk about this again next week more formally. It's called the complement rule, but I just want to kind of introduce this idea now. Okay? Oops. Go here. We'll see if this goes a little bit quicker. Switching. I don't think it's going to. All right, there we go. So we've got our contingency table, right? We've talked about these top 4 left cells are intersections, right? What I also notice is if I take the probability of the intersection of A with B and the intersection of A with B complement, those 2 probabilities add up to just the probability I see A, right? So if I didn't show you these total columns, you could add across the rows to produce the totals, and you can add down the columns. So 0.4 plus 0.1 is 0.5, 0.2 plus 0.3 is 0.5, 0.1 plus 0.3 is 0.4, right? I can add across the rows or down the columns to get those totals, right? So anything about event B here, right? I just add down the column here. Just another example. I kind of mentioned this. I don't think that's too terribly tough. We talked about how we find these intersections, which are just one of these top 4 left cells, okay? So it doesn't matter what I want the intersection of. I just go to that cell. Intersection of A complement and B complement here would be 0.3. So why does adding down the columns and across the rows reproduce those totals? Okay. So I'll try to give you, should be the last thing we have to use the dot cam for, but I'll try to give you an idea about why that's the case. So we had there, if I took adding across the rows, what I was saying was that, this light's on, it's not really helping, hold on, so let me see if I can. Let's say I have this space, And I've got event A here. Okay. And I'm thinking about here is event B. Okay. So if I think about the two areas that I could break A down into, one of the areas would be this area, right? Which, what does that represent? That's where these two events cross over. So this is the probability of A and B, right? It's what's in both of these things. Where would B complement be? Well, if I kind of ignore A for a second, so here's event B. B complement is everything that's not in B, right? So kind of that, if I could shade it in better with a Sharpie, right? You can imagine that area that I just kind of shaded in. So this second area of A, right, if I shade it in here, that's where B complement intersects with A, right? So that blue area is the probability of A and B complement, right? So notice I now have the two components, the two parts of event A. If I add these two together, that should just give me the probability of A, right? So anytime you want the probability of an event, if you take the intersection of that event with your other event and add that to the intersection of that event with the complement of the other event, those two things should just add up to whatever that event was that you were looking at A. And that's essentially what we're doing with that contingency table. When we added across the rows, that's what those two cells represented, right? So we had the probability of A and B and the probability of A and B complement. That's what those two cells were in our contingency table. And that's why when we added them together, we just got the entire area of A, or the probability of A. And just as a kind of maybe reminder, the shaded area, right, we were thinking about, that was our B complement. Okay? Does that make sense? Are there any questions on that? Okay with that?
So the whole circle of A, that's the probability of A intersection of A?
Yeah, so if we want the entire circle of A, right, that would be like adding up the blue and the red areas. So, right, if we just added these together, that should give us, I put the plus sign on the wrong side. That should give us just the probability of A. Any other questions on that? Okay, so that's the general idea of what we're doing there. I think, where are we at on time? I don't have enough time to watch that video. So I would highly suggest trying to watch that video that's in the links. What is it? Wherever, however far back it was. It was the John Stewart link. So I'll scroll back there real quick just to kind of show you. Huh? Just copy and paste it in the bar. Yep. Yeah. It's pretty funny. But the other thing I'll mention is, other than that, whoops. So I had some extra slides in here. We didn't really want to kind of go that far. So these ones, like we're finding the union, and then we're thinking about kind of identifying intersections. We'll start with these next week. We'll kind of come back to these contingency tables. We'll work a little bit more of them, talk about some probability laws, and then we'll probably do a little bit of Excel work. My guess is on Wednesday or Friday of next week, where we start to build our own contingency tables, right? But for now, we're just trying to get used to interpreting them and using them, okay? Any questions for me? Otherwise, we'll get out of here a little bit early. All right. If you have any questions as you're working through those homeworks, make sure you reach out. I've had a couple people do that. Other than that, have a good weekend and stay safe.